Right. So it's yeah, it's recorded now. Oh, and Kantan is coming. Yeah. So yeah, Sophie. Wow. Many. Oh, so.
Good morning, Sasha.
Right. Good morning.
Good afternoon.
Good afternoon. Yeah. Good afternoon. Yeah. Okay. So we start our seminar today. Our speaker is Alan Tassin from FML. Is it right? And Alan is not, it's a seminar of the School of Mathematics at the University of East Anglia. Alan is not a stranger at the university. We worked actually here, not only he, but I and Mark Hooker worked together for, I believe, 2 years. And it was good time. And in particular, it was good because all of us were younger than we are now. But also research was interesting and the topic was very good. So now Alan continues his successful research, leading experiments and also the projects. So just to say before Alan will start his presentation, that this video, this talk is recorded. And later it could appear online in our YouTube channel. We have YouTube channel now, and there are many videos, but not all of them because of the kind of technical difficulties, but also we need to get permission for each speaker to place videos online. However, the link to the YouTube channel is in my last email, so you can go there and check the talks. Could watch them again. So that is where we are now, and now the floor is for Alan. Alan, please.
Okay, thank you.
Start your presentation. By the way, so all speakers, please switch off your microphones and camera. And I shall do the same. So I'll switching my camera, right? And then I'll switch my microphone. So that is the give, say, freedom to Alan to say anything what he wants. And all the questions will be at the end. We have 1 hour for this seminar, but potentially we can stay longer, right? Okay. So I'm switching off my microphone. Alan, please start.
Can you still hear me?
Yes, I can see you and I can see your slides. If something goes on, I will let you know.
Okay, so thank you, Sasha. Hi, everyone. I'm really pleased to be here, as it reminds me also of nice memories. Today, my talk will be mainly on experiments. Also, I'm going to show a few results of modeling. And it's about wave impact experiments on hydrofoil. These experiments were conducted within a larger project. And therefore, there are several contributors to this work. So myself, so I'm Alan Tassin. I'm a research scientist at IFREMER. I got help from Marc Prevosto, a colleague from the Marine Structures Laboratory, where we study the reliability of marine structures. So this work is part of a project where we have 3 other partners, like Ensta Bretagne, and therefore Nicolas Jacques is leading this project, and there are contributions from Romain Asquette and Yves-Marie Scollan. And from the industrial point of view, there are Jean-Charles Poirier and Jean-Jacques Maisonneuve from Sirena Naval Group. And this, so I must acknowledge the support of Agence Innovation Défense and via the ASTRID program and the National Research Agency of France. So this is the outline of my talk. I start by a brief introduction and speaking about motivation. Then I present the experimental setup, the wave impact model, and finally some results of both vertical water impact on calm water and regular wave impacts on the hydrofoil. So let's start. So we are interested in ship appendages and more specifically by hydrofoils, which are subject to water impacts, should be it on submarines, surface ships, but also now you're well aware of the popularity of foils on sailing yachts at any size. It seems to be the new trend. So within the project, we have one main objective, which is to develop a probabilistic approach in order to assess the reliability of hydrofoil subject to slamming. So this includes a global loop, I'd say, starting from the structure characteristics, the vessel operational profile, a given environment from which we will use, use wave and seakeeping models in order to determine impact frequency and probability distribution of impact variables such as velocity, acceleration, relative impact angle, which will be inputs to a water impact model. And this water impact model will be is coupled to a structural model in order to compute the dynamic response of the structure, hence providing information on stress cycle distribution, failure probability in terms of fatigue and yield stress. So in this global approach and in this project, the objectives of the wave tank experiments were to validate some key steps of the approach. First, the water impact model on calm water for calm water impacts, the modeling of regular wave impacts, and finally, impact conditions and force distribution in a given sea state. So today I mainly address the first two points. So let me now introduce and present the experimental setup. So the experiments were run in a large wave tank in Ifremer in Brest. And you see here a sketch of the wave tank. On the right, there is the wave generator. On the left, at the end, you have a dumping beach, and in the middle, we have, two carriages or bridges, which can be moved and which were used to fix the apparatus. So one particularity of this wave tank is that it's seawater, and which is not always an advantage. Here is a picture of the general setup. You see on the left here. Can you see my mouse? Just to check when
yes.
it moves. Okay, good, perfect.
Yes, yes.
And on the right here, you have another bridge, and between these two bridges, we fix this motion generator, which is called a hexapod. And on this hexapod, we have fixed this mechanical system with the foil at the bottom. So here is a close-up view of the setup. At the bottom here, you have the hydrofoil, which is connected to a steel mast via a load cell, which makes it possible to measure the 6 components of force and moment. Behind, you see 3 wave gauges, which are close to the hydrofoil to measure the free surface elevation. And in the back here, you see 2 light sources, which were used to illuminate the wall of the wave tank for the underwater visualization. I'll talk about this later. So here is a sketch, not to scale, of the setup arrangement. It's a top view. In the middle, you have the hydrofoil, which is much smaller than it looks here. It was located 25 meters from the wave generator and 25 meters from the dumping beach. The chord of the hydrofoil was 15 centimeters and the span 42 centimeters. So it's not such a so elongated structure. The leading edge of the hydrofoil was facing the incoming waves. And you see that there's a wave gauge very close nearby. I mean, at the same, it's two-dimensional waves, so unidirectional waves, and we have a wave gauge at more or less at the same distance from the wave generator as the mockup. So here is the definition of several parameters of the experiments, which define the position of the hydrofoil. The first one is the angle of attack, alpha, which is negative when in the nose-up direction. And another parameter which is important is the altitude of the foil of this point here, which over which is the center of rotation of the device, and the altitude is important, especially for the wave impacts. We measure the force. I mean, the principal information is along the z-axis, normal to the foil, Fz, and that's the main results I will show you. And the foil is a NACA 28 profile, which means it's quite thick, 28%. The maximum thickness is 28% of the cord. Here is a picture of the model. Here it's a top view. You see that there are 3 accelerometers, one on each side of the mockup and one in the center, and 2 pressure sensors along the line of maximum thickness. Here is a bottom view of the mockup. You see that we have printed lines and a grid on this surface in order to track to track the size of the wetted surface. And here you see the 2 pressure sensors along the line of maximum thickness. So we used this particular arrangement to track the wetted surface of the foil. This is a sketch of a vertical cross-section of the tank and of the hydrofoil, passing through the hydrofoil. So we had on the left here, waves are coming towards us out of the screen. On the left here, you see the high-speed camera, which looks obliquely towards through a glass window towards the hydrofoil. And the free surface acts as a mirror whose shape changes, of course, and therefore we look at the opposite wall. And that's why we illuminate the wall, the opposite wall. And here you see a picture of what is seen by the high-speed camera when the hydrofoil is not touching the water. But as soon as the hydrofoil enters the water, you see that we can see a darker region where which corresponds to the surface of contact between the water and the hydrofoil, namely the wetted surface. And so you see that we can distinguish the longitudinal or the transversal lines, but we were unable to see the other in the other direction. So here is a sequence of images of what happens during an impact, which starts with the hydrofoil horizontal. The foil first touches the water along the line of maximum thickness. At the early stage, there is the wetted surface increases in both directions. But as soon as the wetted surface attains the leading edge, we can see this bright line here in the front on the left at the leading edge, which indicates that separation starts. But the wetted surface continues expanding at the rear until here on the picture C, where we also see a bright line appearing, indicating that separation starts at the trailing edge. Okay, that's for the experiments. Now I say a few words about the wave impact and water impact model. So here on top left is a sketch of a typical wave impact. The free surface is inclined here, represented in blue, assuming that the chord of the foil is much smaller than the wavelength of the free surface. And assuming a potential flow theory, we can, and the waves are coming from the left, propagating towards the right. We assume that we can decompose the velocity potential into the incident wave potential and a perturbation potential corresponding to the so-called Wagner potential of water impact. For a fixed hydrofoil or fixed structure, the wetted surface condition or impermeability condition states that there is no normal velocity, which in terms of the Wagner potential translates into phi n, so the normal derivative of the potential velocity potential equals to minus the normal velocity potential of the incident waves. And so here we recognize the so-called body surface condition in the so-called Wagner problem, corresponding to, if we look only at phi w, to the impact of a hydrofoil with velocity equal to minus grad phi, the incident wave velocity. So if we look in a reference system tangential to the free surface, Tn, the water impact governing phi w, the equivalent Wagner impact, will be the impact of an inclined hydrofoil with the same angle of inclination, relative angle between the free surface and the foil, but with a velocity equal to minus the velocity, the gradient of the incident velocity potential. And therefore, we can study the impact using the so-called Wagner model, which where the velocity potential satisfies Laplace equation. The free surface condition is linearized on z equals 0 and equal to 0 at Fs, the free surface. And the normal velocity along the body is equal to V n, the scalar product, and with V minus gradient of the incident velocity potential. Based on this assumption, we have to treat the asymmetric water impact of hydrofoil with separation. For this purpose, within the project, in another work package, there was an extension to the fictitious body continuation approximation approach, which was developed for a non-symmetric body. So this approach consists in studying the impact of a body, here a hydrofoil, which we artificially continue or extrapolate with a fictitious body tangentially to the body with a certain inclination angle. And the water impact is treated as if it was a regular body. You assume it's a rigid body entering water, but with a larger size than initially considered. Given that the horizontal velocity has little influence on the little effect on the vertical force, which is the main contribution to the impact, the horizontal velocity is neglected, and the vertical velocity on the body, or I mean on the linearized body condition, is equal to minus the normal velocity of the incident wave. On a region which is either between minus, I mean, on the wetted surface before separation or after. This is why we have max and minus mean here. The pressure is computed by the modified Log-Winovich model by Korobkin, but the hydrodynamic force is obtained by only integrating the pressure over the surface over which the body, the hydrofoil is in contact with water, not on the fictitious part of the body. So you can find more details in this paper by Asquith et al. But in addition to this model, we tried to take into account the effect of gravity, which is clearly present in our experiments. And for this purpose, we used an approach by Wang, Falkinson, and Looney, who proposed a model for to add force contribution due to gravity for a symmetric wedge, with a cavity. The limiting case of beta equal to 0 is a flat plate, and for this particular case, there's a simple equation for the force contribution due to gravity, where C2, A1, and A here are simply solution of this two system of equation, which is simple to solve. So that's it. And now I'm going to show you some results from experiments and models. So first, results for vertical water impact on calm water. So here is an example of a force measurement, vertical force measurement or normal force measurement with respect to the hydrofoil, for a vertical impact at 0.4 meters per second and alpha equal to 0. So angle of attack equal to 0 means the foil is horizontal. The highly oscillatory signal in blue here is a raw measurement, which is affected by the vibration of the structure due to the motion generator. But these high frequency oscillations can be smeared out quite easily by low pass filtering. And here we have applied in green, it's a result filtered applying a cutting frequency of 300 Hertz. In red, you see a comparison between with the MLM, the modified Log-Winovich model, without contribution of gravity. And on this curve, you see two inflection points here. The first one is due to separation at the leading edge, and the second one is due to separation at the trailing edge. We find the same tendency or characteristics on the experimental curve in green here, and we could correlate these events with the apparition of separation on the underwater images, which was very interesting. Just to mention that this red dot indicates when the mockup start decelerating, and therefore there's no attempt to comparison to do between the two models, because it's impossible to. I mean, there is an inertia contribution to the force measured force, and therefore it's not just a hydrodynamic force. Now it's here a measurement for a higher velocity, 0.6 meters per second, with the foil horizontal. Interestingly, we observe much less vibrations at this speed, which is correlated to the acceleration measurements, which are much have a much less smaller magnitude in these conditions. So here we see the same characteristics with separation at the trailing edge and leading edge and trailing edge. But at this higher velocity, we see that the effect of gravity, when at the later stage, when the cavity grows, is smaller. In order to illustrate this difference, we have plotted here the evolution of the non-dimensional force, which is essentially the force divided by the square of the velocity, in order to show the influence of the relative influence of gravity on the vertical force measurements. So here you see the thin lines are experiments conducted 3 experiments at 0.4 and 3 experiments at 0.6 meters per second. In the early stage, the results are almost comparable, but in the later stage, you see that there are a tendency for the smaller velocity results, which tend to increase compared to the higher velocity results, which indicates that there's a growing effect of gravity in the cavity stage. For comparison, we have again plotted the MLM in red without gravity, and 2 CFD results computed by Sirena, a naval group, 2-dimensional simulations with gravity. And although, I mean, during the entire duration of the impact, the CFD results overestimate the experimental results, probably because of the 3-dimensional effects in the experiments, which tend to decrease the force, the total force. However, during the cavity stage, we see that the relative difference between the 2 velocities is rather comparable, and therefore the CFD results seem to predict well this effect of gravity. We've tried also to compare the results obtained with the MLM. So first here you see MLM minus rho GZ, which is just adding the hydrostatic component of Bernoulli's equation to the original MLM. So for 0.4 meters per second, it's a solid a green solid line, and 0.6 meters per second, this blue solid line. We see that there is more or less, I mean, this overestimates the gravity effect on the force. And we have also tried to compare the MLM plus the equation by Wang et al. That I just presented before, which is depicted here by the dotted line in green and blue for the higher velocity. And this version of the MLM plus Wang underestimates the force due to gravity. So now we have let's have a look at the pressure coefficient, which is non-dimensionalized by the velocity square 2. And you see, so that's one of the pressure sensors with again 2 velocities, and a comparison with the pressure predictions by the CFD. It seems that the CFD results overestimate the pressure, but still we have the same tendency at least the CFD results tend to capture the increasing effect of gravity with decreasing impact velocity. However, when we look at the other sensor, you see that there is, in terms of magnitude, the result seems to be quite comparable. But given the difference between the left and right sensor, which are supposed to measure the same thing, it's hard we shouldn't conclude that the CFD results are perfectly comparable to the experiments, but at least it shows that they are able they are able to predict the relative effect of gravity. So now some results for an angle of attack of 5 degrees. So it's a nose down configuration. You see here a compilation of the results obtained for 2 velocities. Similarly to first of all, the force coefficient is smaller in that configuration because the local radius of curvature is smaller. And also we see that separation at the leading edge occurs earlier than before, obviously, because with the impact starts closer to the leading edge. We also see that all experimental results are comparable in the early stage of impact, but again, later in the cavity stage, we see an effect of an increasing effect of gravity with decreasing impact velocity. We have also compared these results with the MLM in red here, and the 2-dimensional CFD results with gravity in blue and brown. Again, due to the 2-dimensional approach, the CFD overestimates the force, but the gravity effect contribution seems to be well predicted. Now we have a look at let's have a look at the pressure coefficient on the left sensor. In terms of experimental results, we cannot say that there is a clear tendency between the two velocity, and almost all the experiments, the results at both velocities are comparable. Also, according to the CFD, we should have a clear difference. On the other sensor, we can see more clearly a tendency between the results at 0.4 meters per second and the other ones at 0.6 meters per second, which seems to be comparable to the CFD approach. However, we observe some very strange behavior of the pressure signals at the early stage, especially at the early stage of the impact. And this is something we've observed in many impacts. As soon as, except for the vertical impacts with no angle of attack, when the hydrofoil hits the water horizontally, we have this negative pressure which appears at the beginning of the impact and which seem to affect the rest of the results too, at an extent which can be much more important than what I show here. Now to finish some vertical with the vertical water impacts. Some results, force results for non-dimensional force results for an angle of attack of -5 degrees, so a nose-up configuration. That's a configuration where the initial water impact force is maximum due to the very larger radius of curvature. But still, in the later stage, at when the cavity forms, there is an effect of gravity. We see the same tendency in terms of comparisons with the theoretical results are similar to what we've seen before. They overestimate the force in the early stage, as in the later stage for the CFD. But the MLM still seems to be closer to the results only because gravity is not taken into account. So we shouldn't, it doesn't mean it's better. So now some results on pressure, similar to, you see here a comparison between two sets of experiments at different velocity. In terms, the experimental results are comparable. There is no effect of almost no effect of the velocity, where we should, according to CFD, we should have won, similarly to the previous results. On the other pressure sensor, we have some kind of difference between the two velocities, but the reliability of these measurements is a bit hindered by what we observe at the beginning and the disparity of the results, the scattering between the different results. So except for the zero angle of attack, the pressure measurements are not that reliable. So that's it for the vertical impact results. Now I'm going to show you results obtained from regular wave impacts. So here is a picture of a wave here, which approaches the hydrofoil. You see that the surface of the waves is rather smooth, except for these small perturbations, which are just due to water droplet impacting the water. In fact, in order to limit the perturbation of the free surface and to ensure that we have a very smooth free surface before the impact, in order to control the shape of the free surface, we use the motion generator to lower the mock-up between two waves. So there is a first transient with 3 waves, a second one, a fourth one, and then between the fourth and the fifth waves, we lower the mock-up. And so now I'm going to see here a movie of an impact, which has been slowed down, of course, in order to magnify the effect. With so the foil is horizontal, and the water impact starts at the leading edge, close to the leading edge. We see that separation starts at the leading edge, then with the wetted surface continues to increase until separation starts at the trailing edge, and then we have a cavity stage. So let me introduce 2 important parameters. So in blue, you see here is represented a regular wave profile. H is the wave height from crest to trough, and ZF is the altitude of the foil here, horizontal. Just to recall that the foil is not at scale; it's been magnified by 3, and so we still have a large ratio between the wavelength and the chord of the foil. So here is an example of a series of wave impact for a 2.25 second period wave. The wave height is 54 centimeters. The foil is horizontal, and the middle plane of the foil is 10 centimeters above the still water level. The thick blue line here corresponds to what we've denoted wave 1. Is the first is the record of the vertical force during the first wave which impacts the foil. And then wave 2, wave 3, wave 4 are the waves which arrive after wave 1 and which successively impact the foil. And so this plot is to show the importance of the consequences of the perturbation of the free surface in the impact curves. Indeed, the wave 1 has a very large peak force compared to the others at the beginning, and has a clear different tendency compared to the other ones. And so that's why we really made an effort to limit the perturbation of the free surface before the impact by lowering the hydrofoil between two waves. Here is an attempt to predict the hydrodynamic force for this particular case. So in order to do so, we have first evaluated the point, the location of the impact between the wave and the hydrofoil, the relative angle between the free surface and the hydrofoil, and the impacting velocity. In addition to the impact velocity, we have also taken into account the acceleration of the fluid particles. Indeed, in red here, you see a prediction by MLM, considering both the initial velocity, impact velocity, and initial acceleration. While in orange here, you see the same prediction, but assuming constant velocity during the impact. And so we clearly see that, especially, I mean, not only in the cavity stage, but that the acceleration of the incident wave particles is important. In addition, you see two curves here. The blue ones is the MLM prediction by MLM plus the hydrostatic contribution term in Bernoulli's equation, which clearly overestimates the impact force in this stage, and the prediction by MLM plus the formula by Wang in the dash dotted line, red dash dotted line here, which probably, as we've seen before, underestimates the contribution due to gravity in our situation. Now I'm presenting here the force, vertical force for the same regular waves. I mean, it's four separate, four different experiments. In these experiments, the foil hits the same wave, but the altitude of the foil is varied. ZF equal to 0, the orange curve here corresponds to the hydrofoil, the middle plane of the hydrofoil equal to 0. So I mean comparable to the still water level. So at the same level as the still water level. ZF equals to minus 50 millimeters means that the hydrofoil middle plane is slightly below the still water level. ZF equal to plus 50 millimeters is above the still water level. And finally, 100 millimeters is further higher above the still water level. Interestingly, it seems that at the altitude of the foil in the early stage only affects, has a very little effect on the force. However, in the later stage, during the cavity stage, we see that for a higher altitude, the force is smaller. And this is probably due to the fact that due to the deceleration, which is higher when you are above the water, the still water level. Now, to finish, I'm going to present a comparison between experiments conducted corresponding to regular wave impact with this configuration and the equivalent water impact on calm water. So for this purpose, we have determined approximately an altitude of the foil with, two configurations with an altitude of the foil, a wave period, a wave height, and an angle of attack of the foil corresponding to approximately here on the right the conditions of impact that we investigated for vertical impact. So you see vertical, we see 0.4 meters per second, which corresponds to what we've investigated earlier. The acceleration is almost equal to 0, and the angle of attack equal to approximately 5 degrees, similarly to our the previous vertical water impacts. And the second configuration is similar, except that it's equivalent. The equivalent configuration is similar, 5 degrees angle of attack, but larger velocity, 0.6 meters per second. So here you see a comparison between two in blue and red, the two curves which are almost superimposed, are two experiments of vertical impact at 0.4 meters per second. And in orange, you see the force evolution as a function of time for the regular wave of equivalent conditions. And so it's very interesting to see that this equivalence is verified, both in terms of initial stage of impact and the cavity stage. And therefore, this validates the equivalence between wave impact and vertical impact. Here is the other configuration for an equivalent vertical velocity of 0.6 meters per second and two similar wave impacts. It's just a repetition of the same experiment. But as you can see, so it's the purple and green lines are really close to each other after filtering, and three experiments which are a bit more noisy at 0.6 meters per second. And here again, until this point where so you see a decrease in the vertical force for the vertical impacts, which is due only to the deceleration of the mock-up, and therefore which cannot be considered as the hydrodynamic component. So this second comparison confirms the validity of the theory. And these comparisons are particularly interesting because so far we had no 3D calculations, computations with gravity. So now I will finish by a few conclusions. So to conclude, first, we've developed a reliable experimental approach, which has made it possible to validate the equivalence between vertical impact and wave impact. The gravity and three-dimensionality of the flow have a strong effect on our experimental results and should be taken into account in order to reproduce these experiments. We believe that the force measurements are really accurate, but the pressure measurements are really delicate, and we still don't understand why we observe such a difference for as soon as the angle of attack is not equal to 0. Especially the occurrence of negative pressure signals. Further work, meaning within the project, will consist in analyzing further the irregular wave impacts. So this is something I was initially planning to present today, but I haven't managed to go far enough. And especially there are some pending difficulties to do so, because we have an important thermal drift of the load cell, because it's a piezoelectric sensor. And so when the water hits the sensor, we have an important, it induces an important drift, low at a longer time scale than the impact, but it hinders the analysis. It seems necessary to analyze the force results in terms of force impulse, because clearly we cannot expect the peak force which occurs at t equal at the initial instant of impact to be well captured by the experiments. I mean, if we want to compare with the model. But in order to do so, the question is raised of the duration of the impulse that we may consider. Another difficulty to compare with the model is to estimate the slope of the irregular waves. But for this, we are working on the free surface reconstruction method, which was proposed by Baldock S1 in '95. And hopefully we'll be able to make comparison with three-dimensional CFD simulations, which are to be conducted by Bureau Veritas with gravity. In terms of longer-term perspectives, meaning out of the project, would be interesting to develop a Wagner model with horizontal speed and separation, maybe with the fictitious body approach. We'd like also it would be interesting to add gravity in the Wagner model for the cavity stage. We've already started implemented a 2D symmetric and axisymmetric version of the Wagner model with gravity. And finally, of course, a three-dimensional Wagner model with gravity would be ideal. And but this remains an open question. And we also plan to do oblique impact experiments, but within another project. Thank you for your attention. That's all I wanted to present today.
Thank you very much, Alan. Thank you indeed. Very interesting, and it's good to see that the experiments and simulations, they are so close to each other, but sometimes close, sometimes not. But if they are not close, then we have extra questions to be resolved. And also that effect of gravity, which is originally was not in Wagner model or in impact model. But if to combine the impact model with gravity and separation, then there could be a wider range of validity of this model, so they can be used for more complicated situations. So, any questions, please? Any questions? Yeah. Any?
Shall I leave the presentation mode? Or?
Yes, please.
Okay.
Yeah. Leave it. So there could be questions about slides. Yeah. Just unmute your microphone if you want to ask question.
Or Sasha, can I?
Yeah. Frank. Yeah. Please.
Yeah. Oh, very nice talk, Alan. Thank you.
Thank you.
Could I just ask what's the typical Reynolds number in these flows, and also do you do you tend to treat or regard separation as meaning cavitation?
So to the first question, I'm too lazy to compute the Reynolds number, but because we are almost sure that viscosity has no effect. As to the second question, we clearly it's not a cavitation. It's an air cavity which forms because the contact point attains the both sides of the mock-up.
Okay.
So it's a separation.
It is separation, yeah, but it is a cavity, an air cavity.
Yes.
It's also in viscous separation. So it's not
Yes.
viscous separation.
No,
Yes,
It's not like separation of so it's more about, could be like Brillouin-Villa condition or the Kutta condition, more like that.
Yeah. Yeah.
Still problem.
Okay. Thank you.
Frank, any other questions? No.
Well,
No.
is there much turbulence around the separation, or in fact the whole flow?
Well, we did not investigate this point, but what has been observed by the people who run the CFD simulations is that because they are solving Navier-Stokes equations, they have to be careful about what they are doing in terms of boundary layer to ensure that there is separation. Because if you're not careful about what happens, you may have no separation at all.
Okay.
Then, meaning that if you have a cylinder, the flow would just flow along the cylinder. There's no cavity forming.
Okay.
Alan, recently some papers were published about impact of bodies with different properties of surface, hydrophobic or hydrophilic, and they claim that because of that, the forces, global forces, are also different. Not much, but still different. Do you think that coating of your hydrofoil could change the forces significantly? I mean,
I suppose that if separation occurs, there is no much influence.
okay.
I mean, but probably that if you are in the regime, because there are two regimes, there is a cavity forming and no cavity forming, and there is a critical velocity above which there is a separation, and so if you are above this critical velocity, I'd say that I don't expect to observe differences, but I have no proof.
So as to Reynolds number, as I understand, your velocities are about 0.6 meter per second, right?
Yes.
And the length of airfoil is 15 centimeters, right? So then as length by velocity, it will be about 0.1 something, 0.1. And then we divide by kinematic viscosity, which is, Frank, as I remember, 10 minus 6. So it will be, Mark Cooker calculated, it will be about 60,000. So 6 by 10 in the power of 4. So it's quite big, okay, not huge, but quite big Reynolds number. That is another question about turbulence. If its Reynolds number is very big, then the turbulence can be important. So that is some difficulties about that. But I have several, two questions by chat. One first question is by Hussein Zikri, our former PhD student, and he published paper, and it should be appear. It's in Journal of Fluid Mechanics on gravity effects on impact. And I believe Hussein could send this paper to Alan. And also, Hussein, I suggest you ask Alan for available, say, data to use for your further research. Hussein is asking, have you found, I'm just adding his question, have you found the correction due to gravity on free surface as well?
No. No. In what we did.
Yes. Yeah.
In what I presented, we just had the hydrostatic contribution, or the simplified formula by Wang.
Yeah. So and then second question by Mark Cooker. Could negative pressure be due to trapped air under hydrofoil? So it's like an air cushion effect or trapped air. So sometimes indeed it's important effect. Do you think it's possible?
So the negative pressure
at the beginning
have a very large scatter, and they do not appear in a consistent way. Especially when we impact, you'd expect the trapped air to be trapped at the location where you first impact, you first touch the water. But it's not the case. I mean, when we impact just at the location where the pressure sensor is, this is the only place when we have no, the only configuration where we have no negative pressures. But I would say I believe it's more a matter of sensor than probably a thermal shock, because the pressures are rather small, and the force sensors are really sensitive to this change of as soon as they touch the water, there is a kind of shock.
Yeah. So I can kind of summarize for mathematicians who are attending this seminar that the equations could be not only to models or to mathematics of the phenomena, but also to experiments, which also are quite sophisticated, and you need to have not only knowledge, but experience and feeling how it works and why it works in that way.
Yes.
Yeah. So let me. There's
a question, Quentin?
Quentin.
Yes.
Yes, please.
Just a question for Alan, coming back to this equivalence between the wave impact and the calm water impact. So you say that this is relevant, but if you come back to your comparison, it seems that it's relevant just for the impact phase. But as soon as you have separation, then you have some big differences.
No.
In the cavity phase.
No, it's related to. Can you see my screen?
Yes.
Yeah. Okay.
Yeah.
Okay.
This type
of, this decrease of force here. So separation. I mean, full separation on both sides starts here.
Okay.
Okay.
I mixed.
And this is separation, the cavity stage.
Yeah.
And here the vertical impact force starts decreasing because I impose because the hexapod decreases, and the mass of the mock-up is so huge. It's made out of aluminium, and that there is an inertia contribution to an important inertia contribution to the force. And the same is valid here for the other impact velocity.
Okay. Thank you.
Just a moment. There is a question from Shaubo. what about the impact force fluctuation before time equal to 0 for any ZF? So before impact, what the Z fluctuations are from? Is it from the sensors or?
It's from filtering.
No, fluctuations before. Yeah.
So, so you have to. So first of all, the model is never addressed, even when it holds still, because both in the imposed vertical motion experiments and during the regular wave experiments, the motion generator is activated. So I'm going to explain a bit more. During the vertical experiments, it's obvious the mock-up is moving, and okay, it's a mechanical system, so there are vibrations. They are very high frequency, but when I filter them, I have some remaining oscillations of the signal. But it's also because of the filter that I use, because it's a pure Fourier filter, and there is a windowing effect. But interestingly, for wave impacts, so we go down between two waves, and then we hold still, and we only have a very low frequency oscillations. It's just because of the dynamics of the control system.
Right. Okay. So, any other questions? It seems no. It seems no. Then, Alan, thank you very much. I would like to point one kind of feature from Alan, that Alan doing or did and doing theoretical research. He is good in analytical modeling. This is what he worked with us at UEA, and he did and doing, as I understand, CFD. At least
no, I'm not doing CFD.
But in your PhD, you did.
Yeah, I did some.
Yeah, once. But also he can do experiments. So that is example of so I would call universal researcher. So that is great. Me and could be some others of participants from UEA. They are not like this. So we can do only equations and modeling. And at the end, let me tell a story, because it seems that I'm a great specialist in the topic presented today. But it's a funny story. It's happened 20 years ago. That time I was in Lavrentiev Institute of Hydrodynamics in Russia, and my director asked me to prove that what I'm doing, I published a paper, what I'm doing is helpful for practice. And I asked my friend of mine in St. Petersburg to contact his to ask his industrial contacts in St. Petersburg to give me some small project, even without money, just to show that there is the industrial contribution from me. And he did, and the problem was about fins. So that is the hydrofoils shown today by Alan. And it was for high-speed boats, just for stability of these boats to prevent roll motion of the boat. So very high speed and very long hydrofoils. And that company contacted me and said, yes, okay, we can do this. Yeah, we give you some drawings, and you can estimate the forces, what Alan did by experiments, and I assume to do on the paper. But after that, they disappeared. And the problem was that they found that their designer, they did mistake. And he or she designed hydrofoil with square cross section. So it's impossible, right? So instead of the hydrofoil, it just was a heavy beam. In that end, they contacted me saying, yeah, you already helped us, so thank you a lot. I asked them, and they checked what they did, and they found, yeah, they just designed it wrong. So then I could report to my boss that I helped to industry in this strange way, doing nothing. It's good to do something. I mean, to get a result doing nothing. But that was a funny story from Never. From that time I worked, and even at that time I did work on hydrofoil. But it's indeed very interesting. Problem, and there are many aspects which were mentioned by Alan at the end of presentation in for future work. And in particular, I believe when we go to practice, then elasticity of these fins are important, and the dimensionality and how these fins are connected to the main how and what's happening at that point. It's not about the performance, I mean, a kind of restoring force by hydrofoil, but also the is it the connection is stiff enough or strong enough so that the ship is not lose its fin during heavy weather. So that is a very interesting practical problem, and just let me congratulate Alan on this nice presentation and nice work done. And let's wait his and his group further results in future. So thank you very much. If any, thank you very much to participants. We had many participants today. Yeah, the bravo from Mark Cooker. To you, Alan. So then we can stay and you can say anything you want, if you want, or any comments, anything. I would suggest just that I stop recording, okay?
Okay.
I stop recording.